Welcome everyone to this talk. So today's speaker is Yoon Hao, and he's the founder of NUTS Technology and a company working on applications of security and cryptography. And in fact, today's talk will be on about encrypting user data in transit and at rest. So thank you to the speaker, and let's see.
Hi, let me just start this slide. So we're going to go through this very quickly today. We're going to cover structured cryptography. And this is a little bit about myself. I used to develop on Wall Street for trading systems, and then I became a trader on Wall Street. And now I'm playing with NUTS Technologies to get some more privacy for everybody. Anyway, here we go. Today we'll cover NUTS Technologies and what we do. Primarily, this is the agenda. We'll define structured cryptography, what it means. Then we'll go through the technology, the origins of the technology, and the problem space that it solves, and then anecdotal stories behind it. It's a little bit backwards, but I wanted to make sure that we hit the technology hard and fast and right from the beginning, and then we'll leave the Q&A for the end. I'm trying to condense this down to a 35 to 40 minute level, and we'll see how it goes. We define structured cryptography as a method of creating modular data structures which allow controlled disclosures by means of decryption-dependent pathways. It sounds like a mouthful, and it is, but we're going to try to cover the technology in some detail and give you the basic idea of what this actually means. So with structured cryptography, why do we want to use it? Why do we need it? Well, the central theme of structured cryptography is that we're using cryptographic security and not programmatic security. So that puts the emphasis on securing things just by using cryptographic data. Primarily, we're talking about keys, and a lot of them. And we're also going to create a framework where it's not dependent on any one cipher, and it'll be cipher agnostic. By doing this, we're going to see that these modular structures become building blocks for creating very, very customizable portable security for data. We're going to cover the technology, which comes in three parts: SDFT, NUTS, and the NUTS ecosystem. Structured data folding with transmutations is a secure messaging protocol, and we're going to go over the essence of how it works. When we talk about the state of data, there's a puzzling dichotomy that presents itself. We know about data in transit, we know about data at rest, and the security of the data in those two modes. Well, how does NUTS approach this? How do we put this together in a cohesive way that doesn't create these separate avenues and separate fields of specialty, nor different ways of thinking about it? Let's take a look at data in transit done in a typical conventional manner. We have structured data here in the form of an address card. And first, we have to transform the data and do any kind of serializations, compressions, encodings, encryptions, whatever you want to do. Turn it into a bit string, and then we start physically transmitting the data. Once we receive the data, we get this bit string again, and then we must undo whatever we've done to the data in exactly the right way, in exactly the backwards way with the right settings in order to recover the original structured data. So let's break this process down. We've done some data transformation functions. We may have put in some applied cryptographic functions to create that bit string. Now, our questions that we had was, can we actually normalize these two types of transformative functions on data, which is data transformation and applied cryptographic functions? And can we normalize it and put it into a framework where they could coexist and interoperate in a very, very modular way and transparent way? We begin by normalizing data transformation functions and applied cryptographic functions into what we call transmutation commands. So the whole idea here is take a typical data operation. If we list them all down, now this isn't a complete list, but it's a large subset of them. And we can classify them, define an operation, and then create a transmutation executable command. And this is how it typically looks. Now, each of these transmutation commands actually has optional arguments. There's a lot of default values that I've put in for it. But with the arguments, you could actually access the 10 flavors of AES that we have commonly out there, the 3 different key sizes that we have, even block sizes and blocking characters. Now, just take a quick look at something like S-Cipher AES, or even if you see this digital signature for using RSA keys. By being able to normalize commands like this, one of the definite benefits that we get out of it is the ability to say, hey, this is an AES 256 operation. I could expect that type of key and key structure. And the other flip side of that is that if I'm not input that key or key structure, I can actually easily create it. So I'll leave you with that. The next step is to create a framework where these transmutation commands can actually interoperate in a very smooth fashion, and we could put a structure around it. So the way we take a look at transmutations is we do this analysis where we take a look at them from a forward mode and then a reversing mode. And as you can tell from the previous table, many of those functions have both a forward and a reverse mode. Now, the ones that we don't have, there can be equivalences, and certain ones you just can't have reverse mode, such as direct hashing or lossy compressions. Anyway, with this framework, what we're able to do is now redefine sort of how a message is actually created. Now that we've introduced transmutations and the concept of forward and reverse transmutations, let's take a look at data in transit using SDFT as the methodology. In this case, with the same structured data, and we create now something called the transmutation audit record, which is just a series of ordered transmutation commands. We name it. We call it a TAR A2. And in this case, we follow these transmutation commands on the structured data, and we call this command the ravel or fold data command. And we fold the data along with the TAR and transmit it. When that message is received on the other end, we know that it is composed of the TAR A2 plus the folded data. So the first step is to unravel that in layer 1 and unfold the TAR, and basically out pops the instructions that created the folded data, and we simply reverse the commands on that data, and out pops the structured data. So the next step, to kind of think about data in transit and data at rest slightly differently, is to think of data at rest as Alice sending a message to herself for some time in the future. Now, it may not be to herself, it could be to other people, so it could be shared. So Alice could be sending to Bob at a later time in the future. But by just looking at it in that way, we can easily see that messaging now versus later, there's really not that much of a difference except time. And this is how we start thinking about SDFT and transmutations as a way of storing data at rest that is really not that much different from sending a message or a secure message down the pipeline at time t. So here's a simple comparison of a data at rest scenario where we'll take, this is using Python, we'll take this data construct, a data structure, dictionary, and use these comments as a guide. and perform the manual data folding. We'll actually fold this data and write it to disk. Now, to read it, we have to undo it, basically reverse the entire process, and then out pops the data string again, or the data structure. When we do it with SDFT, you notice that the comments almost translate right into a transmutation audit record. And this purple area where we're raveling the data structure and then unraveling the data structure are fairly static. And the only variable in this case would be this test A70 transmutation audit record name right here. And we could vary the transmutation audit record on the fly, or just change it whenever we want and just change it by name if we wanted to, or just feed it directly in. And you could see that on the unravel, there is no reference to the tar because it's already embedded in the mydata.json. So you could tell that the coding itself is much more elegant, and we only have to do this in the forward mode. The reverse mode is implied and guaranteed. So we save on errors, and you need a lot less knowledge to code transmutation audit records than to actually perform the actual code. The benefits of SDFT are fairly clear in this brief introduction. The concept of folding the message and the instructions gives it a completeness at a very granular level. We have also designed the protocol to be used for both at rest and in transit. And the transmutation audit record allows for automated key generation and also makes it easier to program with much less errors since you're only doing half the work. It requires a lot less knowledge about applied cryptographic functions, and it allows us to use the knowledge properly by creating very experienced and expert TARs. Also, SDFT allows for incremental eventual upgrades because since the instructions are embedded within the message, you could upgrade them slowly and they are backwards compatible. And that's what we mean by time compatibility, that both backwards compatibility and future compatibility are built in this cipher agnostic framework, which means that it implies that we are going to be post-quantum ready when those new ciphers are out from the NIST post-quantum race. Also, the last thing that I'd like to point out that it presents the concept of a dynamic protocol, meaning that if we're doing a session, I can actually change TARs on a per message basis based upon the sensitivity of the message. And that is something that is very, very rare to find and not so easily done. Now we'll move on to the second layer of the technology called Encrypted User Data Transit and Storage, which is NUTS. And its product is a NUT container, a secure data container. Encrypted User Data Transit and Storage describes a method of creating data with special characteristics. And technically, it is a complex data type partially made of SDFT messages. So you could imagine a JSON structure where parts of it are SDFT encoded messages, all in base 64 encodings. Now, that's a fairly ugly looking structure, but it is actually kind of elegant when you actually see it. One of the main characteristics that we've put in is called the NUT ID. It's a very large number, 512-bit SHA-2 hash, made from various entropy material within your computing environment. So we consider it a practically unique ID, which is kind of a more accurate representation than a UUID or GUID, and it is much bigger. Unlike a UUID or GUID, we consider this a universal namespace and is purely anonymous because we don't put in any kind of structured naming convention like a UUID or GUID. And then obviously it could be independently generated in any manner possible in your computer alone, in your CPU and environment alone. The NUTS technology allows you to create a NUT data structure, and it has now within a NUT structure, it's not just one data structure. There is the modular data structure we call a lock node that a NUT is made of. So a NUT can be minimally made of one lock node, but interesting things start to happen once you have several of these lock nodes strung up together in various ways. Anyway, this is a single lock node, and you could tell that there's several components, but here's the payload, and that's the item that you want to protect and keep secret. But there is essentially 3 layers of security and then this giant keyhole that we have. And we'll go into the interplay of the security mechanisms in the next slide. Let's take a peek inside the lock node at the various layers of security that protect the payload within it. I call this technique structured cryptographic programming. We start with a universal keyhole that supports any number of keys of any type, so symmetric, asymmetric, and passphrase. Automatically, right there, if we use the keys right, we could actually generate multi-factor authentication for the payload, for one lock node payload. Then the next step is what do you do with the keys? Well, the keys interact within this variable lock scenario, and this variable lock mechanism is actually a transmutation. It's described by a single transmutation command that has these 5 different methods of locking: OR locks, AND locks, and secret sharing locks. And they use the keys in the right combinations to get you access into the payload. Now we have this other layer of access control called the stratum access control, which works with universal keyholes and the variable locks of multiple lock nodes. So it really comes into play when you have more than one lock node strung up together. The last layer is what we call our fine-grained access control, which provides role-based cryptographic access control at this fine granularity where we can do insider threat protection by using this verify only capability. And this is all done with cryptographic keys. And this is very, very unique. So now that we know what the innards of a lock node looks like and the various layers of security that's integrated into it, we could take a look at what a lock graph looks like. And technically, a NUT is a lock graph, which is a directed acyclic graph. And a simple one that's linear may look like this, where you have a string of 7 lock nodes strung up together. These are cryptographically linked, meaning that this link it gives a lock ID, which means each lock node has a NUT ID associated with it. And so with that unique PUID number, it would link it with a cryptographic key right into the next keyhole. So the universal keyhole of this lock node accepts a key that's revealed by opening up this particular lock node successfully. And if you open up this one successfully, you'll open up the next one, and so on and so forth until you get to the payload. So there's a lot of decrypting going on in this NUT, but the emphasis here is on the structured nature of this controlled disclosure of different lock nodes as you go deeper and deeper. Now we could control this process with the revealing of the proper keys based upon what somebody has put into here. Now this modularness, and this goes back to structured cryptography, and that is, this is what we mean by it, is within the NUT, we could use these lock nodes to compose these various lock node combinations for different security scenarios. And all of these are possible. They're not hard at all. They don't require programming, and that is the key. And inside the lock node, inside the NUT, all of these things are controlled, and basically they're a complex arrangement of folded messages, folded SDFT messages. So when we coined the term data as the endpoint, what we meant is you put data into a NUT and you lock this thing. That's what it is. It travels with it everywhere. It's cryptographically controlled in terms of access control. It's portable. It has universal protection in any environment, internal, external, hostile, friendly. It comes with its own namespace, meaning that a NUT ID is pretty much universal and kind of unique. And then you could also have other lock nodes within the NUT that carries event logs of what's going on with the NUT, who touched it, what happened to it, and also revision history can travel with the payload. And that's a fairly it's a different way to look at data, and it's almost like a holistic treatment of data. Now, the nice thing about the metadata here is that it's actionable because, first of all, it's trustworthy, and it's basically immutable. It's immutable because we could tell if it doesn't authenticate, you don't want to act on it. Now, you may say, hey, what's the big deal about actionable metadata? Well, remember that we actually have a NUT ID that uniquely identifies, or practically uniquely identifies, this NUT in any namespace. Now we could call it anything else we want in the metadata, but we'll always have something unique to reference it by. That means no more dupe names, name file names, or path names. You'll always have a way to identify this thing. Now we'll cover the third layer of the technology on the NUTS ecosystem. Basically, this ecosystem primarily operates on NUTS, and therefore it operates on secure data. So everything that's in a NUT has a NUT ID. So everything is addressable in a universal way, which is kind of weird to think about it. Not many systems are built this way. And the security is baked in at the lowest levels, and we've seen this with the SDFT layer, that you're actually creating NUT containers using SDFT messages, which is kind of a weird concept. And because of this, the security percolates throughout the ecosystem, kind of in a fractal way, and you also get the benefit of the NUT security. So this is when we start using data structures in a structured security mode rather than creating new applications to do customized security. So how do we do this? Well, so we use NUTs to store secrets. And let's say we create an address book in NUTs, so one address per NUT. And then, if I have a fairly large address book, it may be 20, let's say 200 NUTs. So what? And not only can I put address in there, but I could put passwords, I could put certificates, I could put other NUTs keys that I need to open other NUTs. Isn't this thing called enterprise key management? And PKI is one of the key problems in cryptography and applied cryptography, that we don't have a very good way to secure the keys that keep our data secure. So the NUTbook is what we call a PIM on steroids. And a user can create keys as needed. There's no certificate authority required. And you could also create very, very intricate, very solid personal relationship management systems using the NUTbook so that I could communicate with somebody in a very secure way, in a very point-to-point way, and do this on the fly. So we have this thing called a NUTbook. It is a key management system that is out of this world. You haven't seen anything like this before. So this is what the NUTS ecosystem kind of looks like. So it is every computing device will have, in the beginning, 4 core applications called NUTbook, NUT server, the MEOR server, and the NUT browser. We don't really have time to go over every one of these, but the MEOR basically is a modular I/O repository. You could almost think of it as a NUT-based app, your private app repository. And then a NUT browser kind of looks like your file browser. And the NUT server is the main application that is responsible for indexing NUTs, for talking to other NUT servers, and synchronization and replication of NUTs across systems. The inspiration for this came from looking at data and seeing, hey, when is data really useful? Data is useful when it's organized. And we looked at DNA and said DNA actually organizes data in a organic fashion. So DNA is a great data model. It is the oldest working data model that we know of. It is self-evident. It's about as perfect as we can get it. It's self-healing, self-replicating, self-perpetuating. It uses the environmental resources that it has to help continue its propagation. Uh, and it's absolutely accurate. And so we said, what can we learn from this, right? So here's a technical characteristics DNA that we found. It has identification. We know that DNA IDs, DNA fingerprints. It has complete data. So, you don't have a little piece of DNA sitting at the fingertip and another piece sitting at, your hip bone, and they have to come together to do anything new. That would be disastrous. We wouldn't be alive. It has a sense of history. So when geneticists and DNA biomolecular people rip into DNA, they could tell you some pieces look like fish heads, other pieces look like, lizard tails, whatever. And then we have protection. DNA knows how to protect itself. It creates cell walls. It creates proteins. It creates, other mechanisms to destroy and protect itself and replicate and and heal, or it'll die if it's too sick and it'll replace itself, right? Positional functionality. We mentioned this with the lock nodes. You know, at some point, you had a stem cell that became, a toe cell versus a brain cell. Well, what is that called? It's called differentiation, cellular differentiation. So we said, lock nodes, right? So lock node is a singular data structure that, based upon where it is, it'll act differently. And this is your body is a weird mix of centralized, decentralized, and distributed computations on an organic scale. So we decided, hey, you know what? Let's look at the stuff that works for us automatically, autonomic processes, right? And when you look at autonomic processes, they're very, very deeply distributed and decentralized. So what we like to think about it is, think the paper cut and the healing process, right? So that means if you cut your fingertip on a paper cut, is it really your brain telling it to heal itself, or is it the local cells, because of the release of certain chemicals from that cut, the local cells decide to replicate its cells and repair or replace those skin cells that have been cut. And DNA, from a privacy point of view, is that at a macro level, your thoughts are private. And why is that? We figured that privacy seems to be the natural state of being human. And we coined the term natural data privacy. And if you take a look at our current digital world, the way it is advertised, it is not natural. Absolutely not. So for my thoughts to be conveyed to you, I have to consciously make a decision to enunciate them or write them down, or mime it out. But otherwise, they stay private. So in this way, data is the endpoint, a nut is the endpoint, and now we go to, what does it solve? What problems does it solve? So the problem space of nuts is very large. We've shown that this is privacy by design, almost by definition, and it's privacy by default, and it's for everybody because we created this so that your average user can use it individually for free. Now, we've shown you how a nut using the lock node has fine-grained access control cryptographically built in at the data layer. And we do this by using structured security concepts that we've created. And by doing this, we created a notebook that acts as a universal key management system. And because it's an individual nuts, it's about as robust as you're going to get. And NUTS is all about sharing documents. That's exemplified by the universal keyhole, where it could hold any types of keys, any number of them. That is designed for massive amounts of sharing going on by different participants. And, if you're going to send an attachment by email, well, now if you send an email attachment of a NUT, that's intrinsically secure, and it's basically a JSON file. So there is no programs, there's no viruses in there. If you trust that person, you actually have the key, you could authenticate into it, and hopefully you trust that person to not send you a virus through a NUT. Then you have the data management aspect of NUTs, where the ecosystem using NUT servers does replication and synchronization, and it actually does conflict-free replicated data type supports of any kind practically. So we will do all of that automatically because of the concept and the structure of the NUT itself. This is truly a decentralized and distributed environment, and it's very resilient, very recoverable, and resiliency and recovery is the key to ransomware recovery and then anti-tamper qualities. The centralization aspect of our computing world is kind of concerning these days, because it almost seems to me, from my days of using PDP-11s and other mainframes, that we're kind of moving backwards, like salmon swimming upstream. Problem is, it creates high-value targets, and it also creates the insider threat problems. Meaning, when you create a high-value target, you need administrators to secure it and to manage it. The administrators themselves are insider threats, and not only that, if they are careless with their credentials and keys, they will provide easy entry for external threats to gain control of their systems and leak secrets. And then lastly, the other problem is that we've been shrinking our security perimeter down from networks to devices. Now we want to get down to the data level and actually lock that sucker down. Well, to basically sum up the NUTS technology, we did show that it is practically, it's universally applicable, because everything is about data. Every little thing that we have runs on data, and nothing is useful without the data. So we protect it. And we've built the security at such a low level, and the security percolates and exhibits itself in the same type of characteristics at higher levels of the environment and ecosystem. The data security model within NUTS is very consistent, both internally and externally. The motivation for NUTS was basically my frustration with what tools were available for users. That users are left very vulnerable. They have an inadequate set of tools. They don't interoperate. They're expensive and they're hard to use. I mean, think about it. How many people actually really secure themselves properly on a daily basis? Almost nobody. Even if you're the most paranoid person, you have to be constantly vigilant about doing stuff right. One of the oldest constructs that we have, the file, it needs a change. It needs to change significantly and for the better. And we have reached a hardware inflection point where computing power and storage capacity, we've reached an inflection point. And obviously, we've reached that inflection point with computational and signal gathering technology about 10, 12 years ago, when the machine learning and AI field started booming. Why not data privacy and management? So we gotta kind of pay attention to that. In closing, I feel that the public deserves the best that we can offer as technologists. And we ourselves, as creators and designers of technology, we have to demand more from it. First of all, by questioning age-old assumptions and conventions,
in lieu of new technology is moving so fast that the limitations of what we used to have can be thought out in completely new ways, and those constraints may no longer even matter anymore. The other thing is, let's use our imagination for a better digital world. Meaning, I've seen many, many papers and approaches and thought experiments where we're trying to, save binary data in DNA and organic compounds and basically forcing Mother Nature to do computing in the way we know how to do it in silicon. Well, here, what we're trying to do is maybe we should take lessons from Mother Nature and not the other way around. And maybe nature already knows how to do a lot of this stuff, and all we need to do is really just open our eyes and ask the right questions. So, in effect, nuts is all about the data, and hopefully that kind of explains what we mean by data is the endpoint by using a nut and therefore treating it like an endpoint. Thank you very much.
Thank you, Yoon. That was really good. It was very clear, and it looks like a lot of good information. The way we're going to handle the question and answer, like we've done before, is we try to keep track of the questions for you, and then we'll read the questions to you, and you can see if we can get them answered. So, I have one question up right now. It says, if the file's time has come, is any work being made towards a NUTS file system?
Well, that's a very good question. In my dreams, if we ever get there, we'd love to have a NUT operating system. So if you think about the vector of attacks and the attack surface, take a look at this. A NUT, we could transfer this in clear text in JSON base 64, and you can't open it without the proper keys. And if that's the primary conversation that computer systems have between NUT OSs, you're building in security at a very good level, and it'll be intrinsically secure. And think about an operating system where an application won't be allowed to run unless it comes in an authenticated NUT. What that does is that it removes the entire viral vector. That if the virus isn't smart enough to inject itself in a very sneaky way, but it just appears as an executable, if your system only operates on executable nuts, you're gonna create an entire shield from that particular attack vector. So we would love to do that, and we would love to, entertain any kind of projects that people have interest in trying to take our technology and embedding it at that level.
Okay, that's great. If there are other questions, make sure you put them in the Q&A or let us know you have a question. Right now, I don't see any more out there.
I could maybe explain something about the ecosystem, which I didn't think I won't have enough time to cover it. But
Okay.
in terms of replication and synchronization, our primary concept is that if nuts are identifiable with a nut ID, and a system, a nut server, encounters two nuts that it could open with the same nut ID, guess what? If each nut contains the revision history, we could now create a merge synchronized single version. And that's how we do replication and synchronization in an eventual consistency mode. So hopefully that kind of clarifies the kind of glossing over of the ecosystem and how it does replication and synchronization.
All right. Guan, did you have a question? I see your hand was raised.
I know this is a lot of information, and most people that I talk to they rarely have seen this kind of approach layered in this fashion. So it's a lot of information. That's what I've seen so far.
Okay.
Oh, I see something in the chat.
Oh yes, it just popped up. He's asking, is zero knowledge proof very useful for this approach?
Well, I mean, you got to consider what is zero knowledge proof. If zero knowledge proof is you holding a secret, processing something to prove that you hold that secret, NUT supports that intrinsically, because as soon as you've established secrets that both parties know that you have, but they're not revealed to each other, they could be stored in a NUT. One of our biggest problems that we have in security is, where do you keep all of these secrets? And right now, the most popular password managers, let's say, they would use encrypted tables, right? Encrypted relational tables. We're doing this on an individual basis. So think about the notebook, where every single password, every single address entry is floating around in individual nuts. They're all being synchronized with your own machines within your own home Wi-Fi. No other system does that. That means that I have recoverability to the last updated nut. And even your best enterprise systems, unless they're extraordinarily intricate, won't even give you that. And the only thing that maybe gives you that is everybody uses a centralized cloud storage. So it's a very different way of looking at data and how you preserve data. And why we say that, think about the implications of what I just told you with replication and the notebook is, as soon as you add a second machine to your NUT ecosystem at home, so let's say between your desktop and your laptop, and you got all these like NUTs synchronizing all the time. So I just changed Jerry Hahn's address entry and it gets updated to my desktop. Guess what? If I clicked on a bad link and I start getting ransomware on my laptop and it starts encrypting everything, my NUT server isn't a vector for transmitting that ransomware to my desktop. And I could just shut my laptop down. My desktop is still operational. And I could start using my desktop to recover once I reinitialize my laptop with a fresh copy of the operating system. So in this way, we believe that we're going to deliver to the common user, average person, unbelievable ransomware protection that they've never been able to access before, and in a private way, that none of this is stored in a central server, central cloud. It'll be using your own resources as best as possible.
Okay, are there any other questions out there that we can answer? We have a few minutes on our time, so we're happy to take questions if they're out there.
I like I said, I know that this is a lot of stuff, and it comes from a very different direction from your conventional approaches, and I believe that's why and for people that I've explained this to before, it makes a lot of intuitive sense once you start thinking about how our bodies actually work. And there's a lot to learn from it. And that's what we did, was not to replicate, that we don't want to create the program of life with nuts. What we wanted to do was DNA, we know it works. We don't have to prove it. So can it teach us anything? And what did it teach us? And if it taught us something, can we use those principles to enact a better data model and better data management system? And this is an interpretation of it. And I think it's definitely a different thing on the radar, and gives you a lot of things to think about.
Maybe I can do a very generic question.
Sure.
So, I mean, in my research, I've done some research on situations in which developers do mistakes. So the system in itself could be secure, or the API could be secure, but developers do not use it correctly. So do you see that this technology you're proposing can help developers not to do security mistakes? Because yeah, because I think that's a big problem in security that
Well,
developers.
absolutely. I think there's two areas that we tackle that, and obviously when you make it a very general question of developers not making mistakes, there's all sorts of mistakes they can make.
Yeah,
But the two aspects that we attack very well is when you look at transmutations and the transmutation audit record. You saw that it's very simple and you only have to do half the work, meaning that
yeah,
there's a lot less opportunity for errors to creep in, for weaknesses to creep in. And by doing that, you only do half the work, the other half is guaranteed, and we don't even require you to know the proper way to generate the right keys. So, when you ever first try to run one of these AES or RSA ciphers, you're like, what? They don't even tell you how to create the right keys. You have to figure that out yourself, and what size it is, and then what mode it is. Well, Transmutations just gives it to you. If you don't put any keys into the call, it'll out pop a key stack that you basically have to fold again, and you wrap that up with one key. The one RSA key, with the public key, or the one symmetric key that you have as a secret. So that's one layer that we try to help the applied cryptographer to implement better systems. And then also, you could have the best experts in your organization write the best TARs, right? So you could write, hey, give me 5 transmutation audit records for different purposes. We'll name them this way, and then that's our library, and people will use it, right? And if there's a special sensitive material that requires AES to be done 10 times over in one TAR, you just do it. No, not a problem, right? That's take a look at how long it took to go from single DES to triple DES. You have to change entire systems, entire libraries. Here, you just throw it into the TAR and you're done, right? You do AES 10 times, 20 times, doesn't really matter. Second level is that with nuts and the nut book, we could actually, if I'm a project manager and I control my developers' access to research or development database systems, let's say an Oracle database. In their code, they don't even have to know what server it is, what database it is, what credentials they have to use. I could actually send them nutbook access nuts that contain that information specifically for each individual developer. And what they do is in their code, they read that nut, access the notebook, read the nut, get the credentials, and it automatically logs in. Meaning that all of those attack vectors where you have leakage of code and credentials in GitHub, they're gone, right? You don't have hardwired things. And then moving from development to QA to production, we don't change the application interface at all. It's a change of nut to a particular user. And I know that that user is the only one who could do that because when I share it with them, they have to have the keys to open that credential. And so we're attacking security in that way, and that making it very modular, very consistent, and then not revealing credentials whenever possible by embedding them in nuts. And therefore, when you start using the notebook, you could put in any kind of secret that you want, even the ones that we didn't anticipate, because what is the payload in a nut? It's a JSON structure. So it could be anything, meaning that it's not constrained by how we structured and anticipated a relational table that's rectangular in nature. We don't have to do that. It's just whatever you need to store, you store it and it's secret. And now you could pass it around to different people. So, easier handling of secrets, more consistency. And if you stick it into a nut, there's built-in persistence. across several systems if that's how your ecosystem is set up. So hopefully that kind of answers some of your questions, but
Yeah,
it's not a solve all for everything.
sure. Okay, so do we have other questions? I guess we're
I
good.
don't see any at this time.
Okay.
Okay.
Well, great. Well, I want to express my thanks to the folks at Nuts Technology. We're glad that you contacted us and asked to be a part of of our seminar series. It's been great. In a few days, you'll be immortalized on our website as this
Yep.
recording gets placed out there. So again, I really appreciate you taking the time to come and chat with us today, both to the class and to those of the general public, but also those who will download and view this this presentation, because we do get a lot of hits on these every week. So
Okay.
I appreciate
And
it. Thank you so much.
yes, thank you for inviting, and I really appreciate the opportunity to entertain or educate you.
Absolutely.
Yeah.
Thank you. Goodbye.
Thank you.
Okay.
Okay.
Thanks all.
Okay. Bye.